When an aircraft disappears or experiences a catastrophic event, the global aviation community, along with the public, often turns its attention to a critical piece of equipment, the black box. These devices are paramount in unraveling the mysteries of aviation incidents. However, the popular perception of these vital instruments often diverges from reality. Despite their ominous nickname, aircraft flight recorders are anything but black. They are, in fact, painted a vibrant orange or yellow. This bright coloration is a deliberate and practical design choice, aimed at maximizing their visibility and aiding in their swift recovery amidst wreckage, whether on land or submerged in water. The term black box itself is a historical artifact. Its origins trace back to World War II, a British slang term used to describe sensitive electronic devices, often classified, that were encased in non-reflective black housings. Over time, this colloquialism was broadly applied to aircraft flight recorders, and it has persisted despite their actual bright hue. This initial contradiction highlights a fundamental aspect of these devices. Their design is driven by the imperative of survivability and discoverability, ensuring that crucial data can be retrieved regardless of the severity of an accident. This report will delve into the intricacies of these remarkable devices, exploring their composition, historical evolution, operational mechanisms, incredible resilience, and their profound impact on transforming aviation safety. An aircraft's black box is not a singular unit, but rather a sophisticated system typically comprising two distinct, highly specialized recorders working in tandem: the Flight Data Recorder, FDR, and the Cockpit Voice Recorder, CVR. These two components are designed to capture different, yet complementary, sets of information crucial for accident investigation. Physically, these devices are surprisingly compact and robust. A typical CVR measures around 16 centimeters, 6.3 in height, 12.7 centimeters, 5.0 in width, and 32 centimeters, 12.6 in depth, weighing approximately 4.5 kilograms, 10 pounds. The FDR is slightly larger, with similar height and width, but extends to about 50 centimeters, 19.6 in depth and weighs around 4.8 kilograms, 10.6 pounds. To maximize their chances of survival in a crash, both recorders are strategically placed in the aircraft's tail section, which statistically experiences the least impact force during an accident. Both the FDR and CVR draw electrical power from the aircraft's primary bus system. This power supply is engineered to provide maximum reliability, ensuring that the recorders operate continuously from the instant the aircraft begins its takeoff roll until it completes its landing at its destination. This continuous operation is vital for capturing the entire operational timeline of a flight. While traditionally separate, modern aircraft are increasingly equipped with integrated CVFDR units. These combined units house both audio and data recording capabilities within a single, crash-survivable enclosure. This integration streamlines maintenance procedures and significantly enhances the efficiency of post-incident analysis by ensuring data correlation. The design of these systems, from their dual functionality to their strategic placement and robust power supply, reflects a holistic approach to aviation safety, where every element is optimized to provide a complete and accurate picture of flight conditions. The concept of recording flight parameters emerged from a critical need to understand the causes of aircraft accidents, a necessity that became particularly urgent during World War II with the increasing number of military aircraft crashes. Early innovators laid the groundwork for modern flight recorders. In 1939, French engineers François Hussenot and Paul Baudouin developed the Hussenograph, an early device that recorded altitude and speed data onto photographic film. During the war, British engineers Len Harrison and Vic Husband created a system that recorded data on copper foil, designed for crash survivability. Similarly, in Finland, Veijo Haitala developed the Matahari unit in 1942, which recorded test flight data on photosensitive paper, sometimes surviving impacts. The U.S. Army Air Forces also explored recording cockpit voice data on magnetic wire, demonstrating an early recognition of the value of audio information. The true catalyst for the development and mandatory adoption of modern flight recorders was a series of catastrophic crashes involving the de Havilland Comet jetliners in 1953–54. These disasters often resulted in no survivors or witnesses, leaving investigators with little objective evidence to determine the causes. This urgent need for unbiased data spurred Australian rocket scientist David Warren, working at the Aeronautical Research Laboratory (ARL), to design the first combined FDR and CVR prototype in 1957. His ARL flight memory unit was revolutionary, utilizing steel wire as its recording medium, a technology that became the foundation for subsequent flight recorders. Simultaneously, in the United States, James J. Ryan developed the VGA flight recorder in 1953, emphasizing crash protection by inscribing data onto aluminum foil. Following these critical developments, Australia became the first country to mandate the use of FDRs in 1960. By the 1960s, the importance of these crash-protected devices was globally recognized, leading to their mandatory installation on airliners worldwide. The United States, for instance, made them mandatory in 1967, and the United Kingdom followed suit in 1965 for new turbine-engined aircraft. This progression from rudimentary recording methods to robust, multi-parameter digital systems directly reflects the continuous learning process in aviation safety. Each technological leap, from photographic film and foil to magnetic tape and then to solid-state memory, was driven by the imperative to improve data survivability, increase recording capacity, and enhance retrieval speed and accuracy. The underlying principle is clear: aviation safety is advanced through precise accident reconstruction, and flight recorders are the primary feedback mechanism, constantly evolving to provide more comprehensive and survivable data to prevent future incidents. The core purpose of flight recorders is to provide an invaluable, unbiased account of an aircraft's final moments, enabling investigators to identify the factors behind an accident and, most importantly, to prevent future occurrences. They are widely regarded as the most critical witnesses in air accident investigations. Beyond accident investigation, these devices serve other vital functions, including aiding in pilot training and skills assessment, diagnosing onboard system malfunctions, and evaluating overall aircraft system performance. This broader utility contributes significantly to overall aircraft reliability and the continuous enhancement of aviation operational safety. Aircraft black boxes are composed of two distinct yet complementary units, each serving a unique but equally critical role in providing a comprehensive picture of a flight. The flight data recorder acts as the aircraft's digital diary, meticulously logging a vast array of operational parameters. Early FDRs, mandated since the 1960s, recorded a minimum of 5 basic parameters: pressure, altitude, indicated airspeed, magnetic heading, normal acceleration, and microphone keying, to correlate with CVR information. However, modern aircraft far exceed this basic requirement. Today, FDRs on newly manufactured aircraft must monitor at least 88 important parameters, and many can record over 1,000 in-flight characteristics. This extensive data can include everything from engine thrust and control surface positions, such as flaps and rudders, to autopilot engagement status, hydraulic pressure, ground proximity warnings, and even smoke alarms. This exponential growth in data capture capability directly reflects the increasing complexity of modern aircraft and the continuous demand for more granular information to understand intricate accident scenarios. The FDR operates on an endless loop principle, continuously recording new data over the oldest information. It retains the last 25 hours of aircraft operation, providing a comprehensive timeline of events. This longer recording duration, compared to older CVRs, is particularly useful for investigating incidents or anomalies that might develop over extended periods. The evolution of recording media for FDRs has significantly enhanced their capabilities. Early FDRs primarily used magnetic tape as the recording medium. However, the 1990s marked a pivotal shift to solid-state memory devices, which utilize stacked arrays of memory chips. This advancement eliminated moving parts, drastically improving crash survivability, reliability, and data capacity, allowing for 4 times the data words per second compared to magnetic tape DFDRs. This technological progression has been instrumental in increasing the precision and completeness of accident investigations. The CVR is designed to capture the complete audio environment within the cockpit. This includes not only crew conversations and radio transmissions with air traffic control or other aircraft but also aural alarms, sounds of control movements, switch activations, engine noise, and even airflow noise. This rich audio tapestry provides invaluable insights for investigators, particularly concerning human factors. It can reveal critical information about crew performance, decision-making processes, and potential errors that may have contributed to an accident. The CVR can also capture crucial ambient sounds, such as explosions, rattles, thuds, or stall warnings, which might not be directly recorded by other systems. The recording duration of CVRs has been a subject of significant evolution and, at times, controversy. Older CVRs retained only the last 30 minutes of audio. While modern CVRs in the United States typically retain the last 2 hours of information, operating on an endless loop principle, this 2-hour limit has become a notable point of contention. The European Aviation Safety Agency, EASA, and the International Civil Aviation Organization, ICAO, now require 25 hours of audio for commercial aircraft manufactured after January 1, 2021, with the U.S. Federal Aviation Administration, FAA, proposing to align with this extended standard for newly manufactured aircraft. The resistance to longer CVR recording times, particularly in the U.S., largely stems from privacy concerns raised by pilots and aviation unions. They express fears that extended recordings could be misused for disciplinary actions or surveillance, rather than solely for safety investigations. This tension between the paramount need for comprehensive safety data and individual privacy rights presents a complex ethical dilemma. To address these sensitivities, federal law strictly regulates the release of CVR audio, prohibiting public dissemination and only allowing transcripts of pertinent portions to be released under specific conditions, such as public hearings or when factual reports are officially issued. This legal framework and the rigorous protocols for CVR data handling are direct responses to the need to balance investigative requirements with privacy protections. Similar to FDRs, CVRs have evolved from analog magnetic tape recorders to modern solid-state devices. These newer units store digitized audio information in memory chips, significantly enhancing their durability and reliability, especially in the extreme conditions of an accident. Aircraft black boxes are engineered to endure the most catastrophic conditions imaginable, designed to be the sole survivors of a plane crash. Their entire purpose hinges on their ability to withstand forces that would obliterate the rest of the aircraft, ensuring that the critical data they hold remains intact. The robust construction begins with the outer casing, typically made from highly durable materials like titanium or stainless steel. These materials are chosen for their exceptional strength-to-weight ratio, superior corrosion resistance, and remarkable ability to withstand extreme impact forces and temperatures. Inside this formidable shell, multiple layers of high-temperature insulation, such as thermal blankets and heat-resistant foams, provide crucial protection for the memory units, shielding them from the intense heat generated during a post-crash fire. The core data itself is stored within a crash survivable memory unit, CSMU, which is often the only element of the black box to survive intact after a severe accident. These devices undergo rigorous testing to meet stringent international standards, such as Eurokai ED 112, which dictate their survivability requirements. These tests are designed to simulate the most extreme conditions a black box might encounter. They are literally shot out of air cannons to test impact resistance, subjected to immense static crush forces, and immersed in corrosive aircraft fluids and seawater for extended periods. This meticulous testing ensures that the black boxes can indeed fulfill their role as the ultimate objective witnesses. The following extreme conditions these devices are certified to withstand: fire, high intensity, 1100 degrees Celsius flame covering 100% of recorder for 30 minutes, 60 minutes if ED56 test protocol is used. Fire, low intensity, 260 degrees Celsius oven test for 10 hours. Impact shock, 3,400 gs for 6.5 milliseconds. Static crush, 5,000 pounds for 5 minutes on each axis. Fluid immersion, immersion in aircraft fluids, fuel, oil, etc., for 24 hours. Water immersion, immersion in sea water for 30 days. Penetration resistance, 500 pounds dropped from 10 feet with a 1/4 inch diameter contact point. Hydrostatic pressure, pressure equivalent to depth of 20,000 feet. Once an aircraft accident occurs, particularly over water, the recovery of the black boxes becomes a race against time and the elements. A critical component aiding this process is the underwater locator beacon, ULB, often referred to as a pinger. Attached to each black box, this device automatically activates upon water immersion, emitting an ultrasonic signal at a nominal frequency of 37.5 kHz. The ULB is engineered to transmit its signal from depths down to 20,000 feet, 6,100 meters, and has a minimum operating life of 30 days, providing a crucial window for search and recovery efforts before its battery depletes. Locating these faint, periodic signals, especially in vast and deep ocean environments, requires highly specialized equipment. Towed pinger locators, TPLs, are waterborne devices mounted in hydrodynamic shells, or tow fish, which are dragged behind surface vessels across the designated search area. These TPLs are equipped with sensitive hydrophones that listen for the ULB's ultrasonic ping. Once a signal is detected and its general location narrowed down, more advanced assets like autonomous underwater vehicles, AUVs, and remotely operated vehicles, ROVs, are deployed for detailed seafloor scanning and physical retrieval. These vehicles are capable of operating at extreme depths and are equipped with manipulator arms to recover the black boxes and other wreckage. Despite these sophisticated technologies, recovery can be incredibly challenging. Factors such as ocean thermocline layers, which can reflect sound waves, ambient noise from marine life or underwater gas and oil lines, and the possibility of the ULB being buried by debris can all hinder detection. The search for the black boxes of Air France Flight 447, which crashed into the Atlantic Ocean in 2009, took 2 years, starkly highlighting the immense difficulties and complexities involved in such deep-sea recovery operations. These challenges in retrieving the recorders, particularly in remote or overwater scenarios, underscore the limitations of the current system and serve as a primary impetus for the development of next-generation technologies like real-time data streaming and deployable recorders. Once the black boxes are successfully recovered, they are immediately transported to specialized forensic laboratories, such as those at the National Transportation Safety Board, NTSB, headquarters in Washington, D.C., or India's Aircraft Accident Investigation Bureau. Here, a meticulous process begins to extract and decode the stored information. Experts carefully remove the crash-survivable memory modules, which are often the only intact part of the device, from their reinforced casings. A crucial step in the analysis is the synchronization of the CVR audio with the FDR data. This process creates a precise, second-by-second timeline of events leading up to and during the incident. This synchronized data is then correlated with other available evidence, including air traffic control recordings, radar logs, maintenance records, and detailed wreckage analysis, to construct a comprehensive and objective picture of the incident. With the vast amount of precise data retrieved from the FDR, investigators can generate highly detailed computer-animated video reconstructions of the flight. This powerful visualization tool allows the investigation team to accurately observe the aircraft's attitude, instrument readings, power settings, and movements in the critical moments before the accident, providing invaluable insights that would otherwise be impossible to obtain. The handling of CVR data is subject to strict protocols due to the highly sensitive nature of cockpit communications. Federal law mandates that the NTSB cannot release any part of a CVR audio recording to the public. A dedicated CVR committee, comprising representatives from the NTSB, FAA, the airline operator, aircraft and engine manufacturers, and pilot unions, listens to the recording. This committee then creates a written transcript of the pertinent portions of the CVR audio, which is used during the investigation. This transcript is eventually released publicly, typically at a formal public hearing on the accident or when a majority of the factual reports are made public. This careful process balances the need for transparency in accident investigation with the privacy rights of the flight crew, recognizing the unique and sensitive nature of their workplace communications. The objective, unbiased nature of the data extracted from black boxes, akin to DNA evidence in criminal cases, is fundamental to removing speculation and providing definitive answers, which then directly informs and drives systemic safety improvements across the aviation industry. The information gleaned from black boxes transcends mere historical understanding of past tragedies. It forms the bedrock upon which the future of aviation safety is continuously built. The meticulous analysis of data from these recorders directly leads to critical regulatory changes, the implementation of new training protocols for pilots, and fundamental modifications in aircraft design. This establishes a direct causal loop where accidents, illuminated by black box data, drive improvements that prevent future occurrences. A stark and impactful example of this process is the 1996 ValueJet Flight 592 crash. The cockpit voice recorder captured an unidentified sound followed by shouts of "fire, fire, fire" in the passenger cabin, while the flight data recorder showed anomalous altitude and airspeed parameters. The subsequent investigation, heavily relying on the data from these recorders, definitively determined that an uncontrolled fire in the forward cargo compartment, caused by improperly carried chemical oxygen generators, rendered the aircraft uncontrollable. This direct evidence led to immediate and significant new regulations requiring the incorporation of fire detection and suppression systems in cargo compartments of both existing and future transport airplanes. This was a concrete, industry-wide safety improvement directly born from the insights provided by the black box data. Beyond this specific case, black box data has proved decisive in solving numerous major aviation disasters globally. Examples include the 2015 Germanwings crash, various Malaysia Airlines incidents, and the 2020 Kozhikode crash in India, where the recorders were crucial in establishing pilot decisions and runway conditions. In scenarios where human witnesses are unavailable or physical evidence is destroyed or inconclusive, black boxes serve as the definitive, unbiased testimony, providing the most objective account of what transpired in the cockpit and across aircraft systems. This unparalleled ability to provide factual, second-by-second reconstructions of events makes them indispensable in the relentless pursuit of safer skies. The evolution of flight recorder technology continues at a rapid pace, driven by ongoing regulatory enhancements, the broader digital transformation of aviation, and an increasing demand for real-time monitoring. All these advancements are aimed at further enhancing aviation safety and operational efficiency. The trajectory of future developments points towards a shift from purely post-crash analysis to more proactive safety measures and instant data access. One of the most significant advancements is the integration of real-time flight data transmission via satellite networks. Thousands of aircraft are already actively transmitting in-flight parameters to ground stations as they happen. This capability allows for enhanced monitoring and proactive management of flight operations, enabling remote access to flight data in real time. Crucially, it also significantly reduces incident investigation time by providing immediate access to critical information. This real-time stream also opens doors for predictive analysis and anomaly detection, leveraging artificial intelligence and machine learning to potentially identify issues before they escalate into incidents. Another promising innovation is the development of automatic deployable flight recorders, ADFRs. These units are designed to automatically eject from an aircraft at the onset of a crash, ensuring their separation from the main wreckage. If the aircraft crashes into water, the buoyant ADFR is designed to float indefinitely on the surface and immediately transmit an emergency signal via satellite, drastically improving data retrieval in remote or overwater accidents, a critical challenge highlighted by incidents like Air France Flight 447 and Malaysia Airlines Flight 370. While deployable recorders have been utilized in military aircraft, such as the U.S. Navy's F divided by a -18s since 1993, their widespread adoption in commercial aviation faces significant hurdles, including the substantial retrofit costs and legislative challenges, despite recommendations from safety boards like the NTSB. This illustrates the economic and regulatory complexities in implementing cutting-edge safety technology across an entire fleet. Furthermore, newer models of flight recorders are capable of storing even more comprehensive datasets. FDRs are increasingly able to store over 70 hours of flight data, while the mandated 25 hours for CVRs is becoming standard, capturing detailed information on flight dynamics, engine performance, and even crew actions. Beyond traditional black boxes, some aircraft now incorporate digital video recorders, DVRs, that capture CCTV footage from various aircraft cameras, including cockpit and cabin views. While typically separate from the FDR/CVR, this provides additional visual context to investigations, offering a new dimension of insight into the events. Finally, future recorders will also feature enhanced cybersecurity with encrypted data storage and anti-tamper software, alongside continued miniaturization for improved fuel efficiency and easier installation. These advancements collectively represent an ongoing evolution towards proactive safety and instant data access, fundamentally transforming how aviation safety is managed and improved. From their humble beginnings as rudimentary recording devices, aircraft black boxes have evolved into highly sophisticated, crash-hardened systems. They serve as the ultimate objective witnesses in aviation accidents, providing an unparalleled, unbiased account of an aircraft's final moments. Their vital role extends far beyond merely understanding past tragedies. They are the silent guardians of aviation safety, continuously informing improvements in aircraft design, operational procedures, and pilot training. This continuous feedback loop has been instrumental in making air travel the safest mode of transportation it is today. As technology continues to advance, so too will these unseen guardians. With the increasing adoption of real-time data streaming and the potential for widespread implementation of deployable recorders, the future promises even greater levels of safety and efficiency in the skies. These innovations will further reduce investigation times and enhance the ability to proactively identify and mitigate risks. The engineering dedication behind these bright orange boxes, constantly working to protect every journey, remains a testament to humanity's commitment to safety in the boundless world of aviation.